Welcome. In this video, we look at section 2.7, Properties of Infinite Series. It's not the last section in chapter 2, but it is the last section that we will cover in our videos. This section is all about the convergence and divergence of series. We're going to talk about series. So recall some basics. In a series, we really need to distinguish between the terms of the series, that's the things that are being added together, and the partial sums of the series. That's a sequence where S1 is just the first term, and the second partial sum is A1 plus A2, and the third partial sum is A1 plus A2 plus A3, and so on. And in general, the nth partial sum is the sum of the first n terms of the series. Now, I write that the summation of the series equals A, equals capital A, precisely if the sequence of partial sums converges to A. And I might even say the series converges to A. As a shorthand, we'll just often omit our lower bounds and upper bounds, just as a quick way of writing this. If it's clear what the index variable is, we'll assume that that index variable starts at 1 and goes to infinity. Here's an example. Consider this sequence, and in this case my index starts at 0, 1 over 2 to the k, which is essentially just powers of 1/2 starting at k equals 0. The terms of this series are 1, 1/2, 1/4, 1/8, 1/16, but the partial sums, do you see how that behaves? These are increasing. 1 3/2, so 1 plus a half is 3/2. 1 plus a half plus a fourth is 7/4. 1 plus a half plus a fourth plus 1/8 is 15/8, and so on. And notice that the terms of the series are decreasing while the partial sums of the series are increasing. So it's very important to keep these two different ideas straight in your head. Now, it turns out, in this particular case, I'll prove this a little bit later, it turns out that we can write that this series equals 2, or the series converges to 2, because this sequence of partial sums converges to 2. And maybe you can believe that by seeing where those numbers are going. The sequence of partial sums converges to 2. Here's something that we'll spend a little bit more time on a little bit later. It turns out that this is a geometric series. Basically, it's powers of a number starting with the 0th power. So here on the left in our menu, we see geometric series. We'll talk about those a little bit more in depth. And another thing that we'll see in the future is this series that has pluses and minuses flip-flopping. That's an alternating series. So we have the minuses, minuses, minuses. And we'll see the alternating series test. Let's continue. Maybe the first big result, the first big theorem I have here for series is the algebraic limit theorem for series. So recall, we've seen an algebraic limit theorem before for sequences. So I'm putting it there for reference in the top right. And we will see analogs to this for points 1 and 2 in terms of series. So let's suppose that I have a series that converges to A, and I have a series that converges to B. Then, two things. First of all, if I multiply every term by a constant, then the result is that limit multiplied by a constant, and that constant can be any real number. Also, if I make a new series that adds together the kth term from each of the other series, then the result is the sum of the two limits. And do you see how those kind of look like the results from the algebraic limit theorem for sequences? So we have something similar for series. This number 1, you can think of this as a distributive property for infinite sums. If I know that the series converges, then I can distribute a constant to all the terms, and it just multiplies the result by that constant. And this second one is a little bit like a commutative property for infinite sums. Not the commutative property. I can't just mix my terms around anyway, but it kind of tells me one way that I am allowed to mix around some terms in my infinite sums. All right, some examples here. Let's suppose that I'll take this result I knew from before, that the sum of this geometric series, it might index starting at 0, ends up being 2. Well, then if I multiply every term on the inside by 7, I can essentially pull that 7 out in front, and I get 7 times 2, which is 14. So that's the limit of my second infinite series in there. How about this example? So it turns out, I will not prove this, but it turns out that if I add the reciprocals of the squares, then the result is pi squared over 6. And if I add the reciprocals of the cubes, then the result is, well, weirdly nothing nice. I don't have a good closed form like I did for 1 over k squared. But this has a mathematical notation. We call it zeta of 3, and it's about 1.202. So here are two things that I absolutely know. These things converge, and I know what they converge to. So how about this series? Pause the video right now and see if you can dissect this series and figure out what it sums to. I'll give you a second, and then start the video again when you are ready to check your work. Go to it. All right, welcome back. Let's take a look. So here is that series again on top. I can break it up into two parts, and one part has factors of 9, it looks like, in every term of the series. So on the left, that's just the sum of the reciprocals of the squares. On the right, I pull out a 9, and it's the sum of the reciprocals of the cubes. And so now I can just add together, oh, well, that sum on the left, that's pi squared over 6. The sum on the right, that'll be 9 times zeta 3. And here we go, as an approximation, I get about 12.5. How about a proof? How about a proof for this statement number 1? Why is it that multiplying all the terms by a constant ends up multiplying the limit by a constant? And again, remember our hypothesis. I'm supposing right from the beginning that this sequence really does have a limit. This trick doesn't work if my sequence doesn't have a limit. All right, so saying that the series equals A, or the series converges to A, that is equivalent to saying that the sequence of partial sums converges to A. Sometimes this is what we do. We're given a statement about series, and I translate it into a statement about sequences. Then I use my knowledge of sequences to work. And so actually at this point, I know that in a sequence I can multiply every term by a constant factor, and that will give me the constant factor times the limit. This was my algebraic limit theorem for sequences. There it is up again on the right, and we can see part 1. But now, look what we really have. This guy in parentheses, that is the partial sums for a new kind of series. Do you see? C times Sn is CA1 plus CA2 plus so on up all the way up through CAN. That's the series CA1 plus CA2 plus CA3 forever and ever and ever. So this is just one partial sum of that series. And so that series, that is the sums of C times A sub k, that converges to C times capital A. And it's a similar idea for the proof of 2. We take our statement about the series, we turn it into a statement about the sequences, we use part 2 of the algebraic limit theorem for sequences, and then we translate our result back into a statement about series. There are two great corollaries that come out of the algebraic limit theorem for series. The first corollary is that if I have a series that diverges, then multiplying the terms of that series by a constant isn't going to change the fact that my series diverges, as long as c isn't 0. If c is 0, then definitely it converges. The answer is 0. But if I have a divergent series and I multiply it through by a constant, yep, the result, it still diverges. And my second corollary says that if I have a series A that diverges and a series B that converges, then making the series that adds the terms, that diverges. All right. Thinking about those two things, give this a try. Pause the video, see if you can prove that this series diverges, and then start the video again to check your work. All right, give it a try. Okay, we are back. How did you do? Well, the series that's in the box, that's really just the summation of the constant 1 over 100 times 1 over k. And that thing looks a little bit like my harmonic series, but with every term multiplied through by 1/100th. Now, I know that the harmonic series diverges, and so consequently, the series that was given to us, that diverges also. The Cauchy criterion for series. This turns out to be a useful way to talk about series and their convergence. Again, for comparison, we've seen a Cauchy definition for sequences. A sequence is Cauchy if for every epsilon greater than 0, there's some big N, so that if I go far enough out in my sequence past the big N, then any two of those terms have a difference in absolute value that's less than epsilon. So there's something similar to that in series. Let's see how it looks. The series of A, let's say, converges if and only if, given epsilon greater than 0, there exists some big N such that N and M greater than capital N, and also I'm requiring little n bigger than M. If that's the case, then that implies that this absolute value of the sum a sub n plus 1 through a sub n is less than epsilon. This looks a little bit weird, but this ends up being a very useful tool for us in a lot of proofs that we'll see coming up soon. Okay, so maybe pause the video if you need to and kind of think about that for a second. Where in the world does this strange summation come from? And in the proof, we will see exactly where it comes from. So here we go. The proof is very easy, not bad. Our series converges if and only if the sequence of partial sums converges, and we know that a sequence of partial sums converges if and only if that sequence of partial sums is Cauchy. So let's think about what it means that the sequence of partial sums is Cauchy. It means, given that epsilon is greater than 0, there exists some big N such that, again, little n, little m greater than or equal to the big N implies that the difference of my partial sums in absolute value is less than epsilon. Now this is where this strict greater than comes in handy. It's not really required, but we're in the situation where m and n are both greater than big N, so I might as well just label them so that little n is the bigger of the two, right? So little n is the bigger of the two. Then when I take my s sub n minus s sub m, I get this sum of the a's. Do you see that? Here's my s sub n is a1 plus a2 plus dot 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 plus a sub n. And if I take that and I subtract off a sub 1 plus a sub 2 plus dot 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 plus a sub m, what remains? Well, the n is bigger. So all of the terms a1 through am, they disappear. And the only thing that remains from my initial s sub n, my initial partial sum with n terms, are the terms m plus 1 through n. So in this Cauchy criterion for series, this sum that we see at the end in terms of the terms of A, that's really just a difference of two partial sums. A simple test for divergence. Here we go. This is pretty useful. If a series converges, then the sequence of its terms has to go to 0. And the contrapositive is very useful. It's a good way to think about it too. Suppose I have a sequence of terms that doesn't go to 0, right? Imagine maybe I have a sequence that, well, say maybe it converges to 1/2. You know, down the road, all the terms kind of look like 1/2. If I make a series with those terms, certainly that has to diverge. Imagine, you know, towards the end, I'm just adding 1/2 plus a half plus a half plus a half forever and ever and ever. That has to diverge. The only way that a series can converge is if its terms actually shrink down to 0. All right, so let's see why that's so. I mean, it seems reasonable, but here's a little proof. Suppose that my series converges. All right, now what am I trying to do? I'm trying to show that this sequence converges to 0. The sequence of terms converges to 0. Let epsilon greater than 0 be given. There is some big N, so that whenever little m are greater than or equal to that big N, it follows that this summation in absolute value is less than epsilon. That's exactly our Cauchy version of saying how a series converges. All right. Well, then what do I do with that? That statement is true for any n and m greater than or equal to the big N. So in particular, let's just let m be chosen. Just choose some little m that's sufficiently large. And my little n is just going to be just one more than that little m. Well, what does that summation look like in this case? Then it turns into simply the absolute value of a sub m plus 1. And I know that that term of my series has to actually be less than epsilon. Well, in fact, that little m was chosen somewhat arbitrarily. I could choose any m that's greater than or equal to big N, and I can take my little n being one bigger. So in fact, we get the following result, that I can prove that for any term, any kth term of my series, that thing in absolute value has to be less than epsilon. So in fact, all the terms of my series shrink down to 0. One big warning. The converse of this theorem is not true, right? The theorem says that if the series converges, then the terms diminish to 0. But what do we know? We've seen something like 1 plus a half plus a third plus a fourth. Here's our harmonic series. And what do you know about this? The harmonic series diverges, even though its terms diminish to 0. So it's not enough knowing that the terms diminish to 0 in order to say that the series converges. It just isn't so. So if the series converges, then the terms diminish to 0, but the converse is not true. The comparison test. I'm going to put a star by this. This is maybe our most useful test of all. How can I tell if one series converges or diverges based on what I know about a different series? All right, so suppose I have two sequences. These are going to be terms in series. I have an A sequence and a B sequence. Both of these numbers are always positive, so the terms of my two sequences are always positive. And B is like the bigger one. So B for bigger, and A, what is A for? A for small. There we go. So A is the smaller and B is the bigger. And let's make series based on our sequences for A's and B's. If the B series converges, then the A series has to converge also, right? This is the big one. If the big series converges, that means I add up all these terms and it turns into some actual number. Well, the A's are smaller, right? So if the big series adds up to an actual number, then surely the smaller series is going to add up to something smaller, and they're all positive, right? So the A is kind of squeezed in between the 0 and the B. And then we have the contrapositive of that. If the small series diverges, then the big series has to diverge as well. So if I add together a bunch of small things, but those small things end up growing and growing and growing without bound, then surely, if I add together things that are bigger than that, then that new series must diverge as well. So that is our comparison test. Let's see an example here. Can you do this? Maybe think about this for a little bit. How would you compare this to a different series in order to prove that this guy in the box actually diverges? Take a second, pause the video, and give it a try. Then start it up again when you're ready to check your work. All right, let's see what we can do. Maybe you found something like this. Here's an example of a smaller series, and by smaller I really mean term-wise. So when I'm comparing terms on the bottom and terms on the top in the same place, every term on the bottom is smaller than its corresponding term on top. But this guy on the bottom, does that diverge or converge? I'm looking for something that diverges. And it does, because that series down there is really like 1/3 times 1 over k. Now, I know that the harmonic series, 1 over k diverges, so certainly multiplying through by 1/3, that's also a divergent series. So there we go, our smaller series diverges. And so the larger series diverges as well. How about a proof? This is really just a sketch of the proof, the big idea. And how I think about it is that I have this sum of terms, a sub m plus 1 through a sub n. And since I have this comparison, 0 less than or equal to a, less than or equal to b, then it has to be the case that that sum of a's is less than or equal to that sum of b's. But that's exactly the sum that was a central part of determining whether the sequence converges or diverges. So I'll not go through the details, but that's the big idea, and then we can follow the Cauchy criterion for series to get our results. One quick observation is just to remember, we compare the series term-wise, just term by term. All the terms are positive. All the terms have to be positive in order to use this comparison test. And one other thing is actually that the comparison needs to only be eventually true. Maybe the first 100 terms of the sequence don't really compare well. Some are bigger, some are smaller, it doesn't matter. But after the first 100 terms, then you have this consistent comparison where one sequence is always bigger than the other. That's sufficient. As long as we have a comparison of the series eventually, then we can use the comparison test. All right, let's turn our attention to geometric series. Geometric series is a nice family of series that gives us lots of good examples of series that converge. Here we go. To start actually with an example, consider the powers of 1/3, starting with the 0th power, or the powers of 5, starting with the 0th power of 5. Well, this guy on top, I think there's probably some hope that it will converge, right? I mean, these numbers look like they're getting smaller and smaller and smaller. Now, that's not sufficient to know that the series converges, but maybe it does. Maybe it converges. It looks like these terms are going to 0 much faster than the terms of the harmonic series. This guy in the bottom, no, there's no way that that guy converges. If I have a number, bigger than 1 and I keep adding it again and again and again, that will diverge to infinity. In general, if I sum the powers of some number r forever and ever and ever, will that thing converge? Will it diverge? And here's our answer. If r is strictly between 0 and 1, then the summation of the powers of r, indexed starting at 0, turns out to be 1 over 1 minus r. That series converges, and it converges to that number right there. Here's the proof. The hardest part of this proof is actually this first line here, and it's just algebra. So maybe you need to take a minute and convince yourself. It's kind of curious. If you multiply these two factors at the beginning, they simplify beautifully to become simply 1 minus r to the m. And then divide both sides by 1 minus r. So we get this summation, 1 through r to the m minus first power is this fraction. And now, let's imagine taking the limit as my m goes to infinity. Basically, I'm taking the limit of both sides, thinking of these as sequences. On the left, what happens when I take the limit as m grows without bound? Oh, that's just exactly our infinite sum. And on the right, what happens to this limit, what happens to the right-hand side as my m grows to infinity? Well, r is between 0 and 1, so that shrinks to 0. And I'm left with 1 over 1 minus r. So take the limits of both sides and use the algebraic limit theorem for sequences, and we get our result. How about this? What is the sum of the sequence at the top, the one in the box? All right, pause the video and use our fact and see if you can find what number that converges to. Okay. And where does it converge? It converges to 1 over 1 minus 1/3, which happens to be 3/2. Here's the more general setting for a geometric series that we sometimes see. Instead of just powers of r, I might multiply through also by some number a. And if a equals 0, then this series converges no matter what r is, right? Because a just wipes everything out. The answer is 0. That's the boring case. If a is not 0, then this series converges precisely when the absolute value of r is strictly less than 1. So this more general case we can also consider the situation when r could potentially be negative. Now, when it does converge, where does it converge to? It converges to the number a over 1 minus r, which really looks like the 1 over 1 minus r that we had on the previous slide, but just multiplied through by a. give this a try. Here is a series here. Prove to me, prove to yourself, do it for yourself. Prove to yourself that this guy converges. Pause the video, see if you can do this, and then start up again to check your work. So, how did you do? Well, did you compare it to a geometric series? Here is a larger, term-wise, here is a larger series, and it is a geometric series. It's the series that is powers of 1/2. And if I do my my trick here, 1 over 1 minus 1/2, the answer is 2. That converges to 2. So since I have a bigger series that converges, I know that my smaller series must converge as well. The absolute convergence test, another test to determine whether a sequence converges or not. To begin, let's just think about this. I have some arbitrary series, and I want to compare it with that same series where all the terms are given in absolute value. So my original series could have pluses and minuses in it, but after using absolute value, it's definitely all positives. So here's the question. If you had to guess that one of these was going to diverge and the other one didn't, which one would diverge? Would the regular series diverge, or would the series of absolute values diverge? And you're thinking to yourself, if only one of them diverges, it's going to be, yeah, the one with the absolute values. Because when I don't have absolute values, the terms might have pluses and minuses, and there could be some canceling that goes on. It never really gets too big or too small if the negatives and positives balance each other out. But with absolute values, the series can only grow positive, positive, positive. It can only increase more and more and more. And this is the idea behind the absolute convergence test. If the series in absolute value converges, then definitely the series without the absolute value converges also. Here's an example. Here's an alternating series, 1 minus a fourth, plus a ninth, minus a 16th, plus a 25th, and so on. Does this thing converge? Does it diverge? Well, let's say I'm not too sure, but let's look at the series in absolute value. After applying absolute value to every term, I get the series 1 plus a fourth, plus a ninth, plus a 16th, plus a 25th. Oh yeah, and we've seen that series before, and we know that series converges. In fact, it converges to pi squared over 6. And since the series in absolute value converges, it seems reasonable that when I throw some pluses and minuses in there, then the original series would have converged also. All right, let's see a proof. I start by assuming that the series in absolute value converges. What does that mean? Let's go to our koshi criterion. Given epsilon greater than 0, there is some big N, so that when little n greater than little m greater than or equal to this signpost big N, if that's the case, then I know that this sum in absolute value is less than epsilon. Now, officially, do you remember in koshi, we had another bar around it, the absolute value, but since all of these guys are absolute value anyway, we don't need those outermost bars. And now, I can apply the triangle inequality, but I apply it actually backwards a little bit, because if the sum individually is less than epsilon, then I can get something even smaller. By putting the absolute values around everything, triangle inequality tells me that this second expression is smaller than the one above it. So it too must be less than epsilon. And that is enough to tell me that the original series converges, because that is the Cauchy criterion for a series converging. So a short proof. If my series converges, and that series in absolute values converges, we say that my original series converges absolutely. So do you see that on the screen here? Here's that example right there. The original series converged, and the series in absolute value converged. And so that series that I started off with originally, we say that series converges absolutely. It's a very It's a very strong requirement on convergence, that it converges absolutely. Now, there's a weaker kind of convergence. If, say, that I have a series that converges, but in absolute value it diverges, that's a little weaker. I mean, the series still converges, to be sure, but in this case we say that the series converges conditionally. What might be a sequence that converges conditionally? Maybe something like 1 minus a half plus a third minus a fourth plus a fifth minus dot dot dot. It's the harmonic series, but alternating. And it seems reasonable that this should converge. I haven't proven it, but it seems reasonable that this should converge, and it does. But in absolute value, it does not converge, it diverges. So this sequence that I have here at the very bottom of the screen, that sequence converges conditionally. Well, in fact, I'm basically going to revisit that sequence again, that alternating harmonic series, because it's a special case of the alternating series test. Here we go. If I have a sequence where all the terms are decreasing and all the terms decrease to 0, so in fact they're all positive, then the alternating series converges, where I stick negative ones in front of every other term. For example, I mean, the big example of this is the alternating harmonic series. Sorry, by 1 and 2, each term is positive. The alternating harmonic series. So how about 1, 1/2, 1/3, 1/4, 1/5, 1/6. So there's my sequence of A's. This sequence is decreasing, and all of these things are positive, and it converges to 0. Then, if I create a sum of that, and I alternate my pluses and minuses, so 1 minus a half, plus a third, minus a fourth, plus a fifth, minus a sixth, on and on, then the alternating series test, that tells me that this guy will converge. Proof is omitted. Well, that brings us to our last result, and it's a big result, and it's kind of cool. I mean, it's big in the sense that it's really fascinating. If a series converges absolutely, then any rearrangement of this series converges to the same limit. Now, what do I mean by a rearrangement of a series, a rearrangement of a sum? That's when all the original terms appear eventually, and no term is repeated. That's a rearrangement of the terms in a series. In 2.1, we saw an example of a series where if you rearrange the terms, you get a different sum. But this result is really what tells us when that fails. If the series converges absolutely, then there's our safety guard. This is what will ensure to us that every rearrangement of the series really does converge to the same limit. A series converging absolutely, that's what guarantees that the commutative property holds in an infinite series. The proof for this is a little bit long, and it's more complicated. There are more details than I really want to get into. So at this point, I'm actually just going to say, if you want to stop the video, this is a good place to stop. Otherwise, I will go through the proof silently, revealing the lines, and you are welcome to take your time and enjoy reading through the proof of this result. Let us begin. There it is. You've reached the end of our final result, and that brings us to the end of 2.7.